Brought to you by Chemistry.
Hi everyone and welcome to Brought to you by Chemistry. What's brought to you by Chemistry, I hear you ask? Complicated reactions? Complicated exams? Even more complicated romances? Yes, but in this case it's also a podcast series from the Royal Society of Chemistry, so you see the branding there. My name is Dr. Alex Lathbridge and we're fully charged because in this series we are taking a look at batteries, bringing together experts from inside and outside the world of chemistry to help us understand the ins and outs, the positive and negative, the ups and downs of all things batteries. So, I am going to start with you, Isobel. Could you please introduce yourself?
Yes, of course. Hello, I'm Isobel Sheldon. I'm the Chief Strategy Officer for Britishvolt. I was the first person in the company with our CEO and founder, Oral Najari. And I've been involved in the battery industry for just a little over 20 years now and was responsible for some of the first batteries, lithium-ion batteries, going into electric vehicles and plug-in hybrids.
Mauro, please introduce yourself.
Hi, I'm Mauro Pasta. I'm an associate professor in the Department of Materials at Oxford. And I'm also the project leader on one of the Faraday Institution projects on solid-state batteries. And I'm sure we'll touch on solid-state batteries today.
Look at that. I love that you're doing my job. I'm sure we'll talk about this. Now we're not going to. Do you hear that, Isabel? We're going to completely ignore solid-state batteries.
It's going to be hard.
I guess my first question is to you, Isabel. I mean, what do you think? I mean, what are the problems that with current batteries that we're trying to solve with future batteries? I mean, what are the issues? Because I think batteries are pretty cool right now.
Yeah, batteries are pretty cool right now, and they've got to a level of performance and capability that means that they're practical and useful in vehicle applications. That wasn't always the case in the past, but certainly we're getting to the kind of range figures that are really quite acceptable for mass adoption. So, you know, if you're getting into 300 miles or even 400 miles range in some cases, then that's covering, you know, the vast majority of people's usage profiles. So I think, you know, the trick in the future is to look at things like vehicle efficiency. We could always do with them lighter and smaller. We could always do with them at a lower cost to improve the price point access for people who walk in showrooms and buy cars. But certainly one of the real big things that we're working on as a company and we're trying to solve is the embedded carbon content in the supply chain for batteries. Yeah, I think it's been proven that electric vehicles are better for the environment with the existing supply chain, but there's a significant opportunity to remove more embedded carbon out of those materials to make sure that we get to the most sustainable solution we could possibly have, because at the end of the day, this little blue marble we all live on is the only known place in the universe where life exists, and we've got to start taking a little bit better care of it.
I mean, Mauro, did you enjoy, like me, how that was super optimistic about batteries? And then there was a little reminder at the end that we have very little meaning to our lives and we have to take care of this planet. I like that. It was a hard sell. I love it. All right. So keeping that going. I mean, Mauro, in terms of batteries, I mean, can you tell us from your perspective, I mean, what are the next generation of batteries that you're working on? Because I want to know, how do we get to this future that Isabel's talking about? How do we get there?
I mean, let me just start by saying, I think you introduced that as well, right? I mean, there is nothing particularly wrong with the current lithium-ion battery chemistry. So it's at the core of the electric revolution that we're all experiencing. What we are looking at is to try to improve the lithium-ion battery chemistry on a few metrics. Isabel touched on a few of these already. We're trying to increase energy density, so the amount of energy you can store per unit volume or weight. That's important for range. Isabel touched on range. We like to extend it if possible even further. Flight time, an electric flight, for example, that directly correlates with, are you intrigued by flight time? Yes, you know, that's one of the future applications, electrification of flight. And energy density, particular gravimetric energy density, correlates to flight time, or how long, you know, your plane can actually be in the air. We're trying to also decrease as much as possible the time required to charge our battery, which is one of the perceived problems, especially in the EV sector of the normal user, right? So you see if we can get closer to the time required to fill a tank, like in the order of 10 minutes. And again, cost. And cost has different components, I would say. Industry has done a great job in the past, probably 10 years or so, in driving this cost to where it is right now. But still, if we want to empower this electric revolution to the full extent, we would probably like to decrease this cost even further. And this comes down to cost and bill of materials. So the raw materials that we use to make batteries, their supply chain. We're familiar with issues with supply chain all over different industries, these days, as well as recycling. So we are looking at chemistries that would be able to help on ideally all of these fronts or some of this, right? And I'm not sure if you want to touch. Maybe let me mention a couple of chemistries we're particularly excited about.
Yeah. So come on, this is a chemistry podcast by the Royal Society of Chemistry. All right, let's give people what they want. They want the chemistry.
So I think definitely the implementation of metallic lithium as a negative electrode, which result in increased energy density I was mentioning earlier. Ideally, we would like to do that in a liquid electrolyte if it was possible. Right? That will allow us to take advantage of the current manufacturing process of lithium-ion batteries, right? But it turns out that it's quite challenging to cycle lithium metal in a liquid. It doesn't like to plate and strip very uniformly. So you form what these filaments that grow all the way through your separator, pierce your battery, end up in catastrophic failure that we've all seen, fire, et cetera, et cetera. Hence, there's a big push recently on replacing the liquid with a solid in solid state batteries. So by replacing the liquid with the solid layer, and we'll talk about what solids maybe if you're interested, we could in principle implement the safe implementation of lithium metal. So increase energy density. In principle, again, I keep saying in principle because we have some fundamental challenges still that we need to tackle and solve. In principle, also charge and discharge the battery in the order of the 10-15 minutes that we're all hoping for. And at the same time, again, if we figure out manufacturing challenges, maybe decrease cost as well. So that's why solid state is perceived as one of the most exciting chemistries. I'm also working on what I mentioned earlier, the problem of raw materials. So see if we can work on chemistries that do not require some of the most critical elements that are currently used in lithium-ion, starting from nickel, lithium itself. So to see alternative to lithium, particularly excited about potassium ion, for example. So these are the two main areas that I'm particularly interested in.
Okay, so for me, that's proper interesting. Something's making me think about the future, and I honestly haven't considered a lot about the future. When I see batteries now, I'm not thinking what will batteries look like in 10, 20, 30 years time. I care about whether or not my computer will run or whether my fire alarm will continue to save me. Wow, that sounds really dark. Sorry, Isobel, you've got me in a really pensive mood about the future of my existence. So I do care about batteries and my smoke alarm. But we sort of talked about the futures and potential futures there. But in terms of more concrete stuff, Isobel, what's Britishvolt working on at the moment? Because I've heard that you've got a new gigafactory, and I have no idea what a gigafactory is. Tell me, what's a gigafactory and what are you doing with it?
Well, this sort of dovetails nicely with what Mauro's just said. There's an exciting future with lots of interesting materials that need to be developed and proven to work, and some new manufacturing methods to be able to produce those and get those into commercial scale so that we can deliver products that are going to be the kind of products that people will buy. And again, he's absolutely right that EVs is just one part of that. There's an awful lot of the economy that needs to be electrified, and aviation is a future one that we should be focusing on. But it's important to understand that some of these developments are quite a way off in the future. We're not going to have solid state batteries by 2024 or 2025. You can Google an awful lot of information on the internet that will have you believe that it's imminent and it's going to happen. And why should I buy an electric vehicle today when it could change next week? In reality, that's not going to happen because of the reasons that Mauro has pointed out. Using a lithium anode is a big challenge. They're avoiding problems. There are plating and dendrite problems. There's stability problems that need to be overcome. So what we need to do is really need to focus on the foreground. So lithium-ion battery technology has come along in leaps and bounds over the last 20 years. All started with lithium nickel oxide, went on to lithium cobalt dioxide. We moved into the mixed metal oxides, the NMCs, and we've increased the content of the nickel as time goes on, so that we don't have to rely quite so much on cobalt. We have an emerging resurgence of LFP technology, which is finding an application on the lower end of the cost scale. So these are the technologies where we need to really focus in this shiny new gigafactory that we're going to be launching in early 2024 up in the Northeast. And understanding that there's headroom left in lithium ion. There are things that we can do to improve energy density incrementally over where it is today. We don't need to completely reinvent the manufacturing process. We can optimize it and we can improve it. We can use less energy in the manufacturing process. All these things are good things to do, but fundamentally, to fuel this growth in electric vehicles and the demand profiles that we're seeing. And don't forget, all these demand profiles have come forwards from 2030 to 2025, and you can see all the automotive OEMs are announcing cycle plans and a big transition to electric vehicles. It's utilizing the headroom in what we have available to us today to improve the state of the art of the products that we can get out onto the markets and put things in the consumer hands that really do meet those range requirements or meet those price points that they want to buy these vehicles at.
Okay, so like both of you have touched on it, and I'm going to jump straight into it with this question. And this is a question for both of you. Are we going to see electrified flying vehicles? Because when I think about electrified flying vehicles, I'm like, that's something for 100 years, 200 years time. But both of you, both experts, are both talking about it like it's, just a standard thing. Like one would talk about the weather or a Vauxhall Corsa. So what's this? What's going on? Electric vehicles? One of you, both of you, tell me about this. Electric flying vehicles, tell me about this. What is this?
You want me to start, Isobel, maybe? Just a few points on my end. I mean, it depends what you mean, right? The electrification of flight means a lot of different things, right? You can go from drones or what they're usually called unmanned vehicles. So like smaller, again, drone-like vehicle that allow to, for example, carry packages or small goods, and that are already here. We're already testing them on a day-to-day basis. So it's already here. But the question is, probably that's what you're thinking about, passenger flight. That will require a substantial amount of work in terms of battery chemistry, again, increasing energy density substantially. So it's not going to come very, very soon, but it's something that we're aiming for, again, when we look beyond lithium ion. And there's all sorts of an intermediate level, right? Shorter range flight. Again, what we care about is range. And with the current lithium ion battery chemistry, we are limited. But what we're working on, and again, looking more in the future, our chemistries will allow us to empower these longer flights.
Yeah, I agree with Mauro entirely. But I do think that there is something in the foreground that is almost starting to get to where it needs to be, and that's the eVTOL type application. So, going very short distances between cities, sort of 70 to 100 miles. We're almost there, with passenger flights going into the air and not just rolling along the ground. And this is an important step because we have major congestion in our major economies around the world. The roads are chocked up. We'll just end up replacing those with electric vehicles at some point in the future, and we'll still have the traffic jams. So we need to start thinking about how we can move transportation away just from the surface and into the air. And eVTOL is the first step. And there are a number of companies that have already demonstrated capability in this area. There is a certification loop that needs to go through, and the authorities around the world are looking at that and how to make that a little bit easier. But at the end of the day, we've got to look after safety, and we've got to make sure that anything that flies that's run on batteries is as safe as it possibly can be, because you can't just pull over at the side of the road and step out if something goes wrong. It's a little bit of a different safety case at 30,000 feet. Well, it won't be 30,000 feet for eVTOL, but it certainly won't be on the ground. So we're already making tentative steps into this. So Mauro is absolutely right. If we want to replace some of the more common forms of air transportation, short haul and long haul flights, there's a huge amount of work to be done. I think if you want to fly from London to Paris on a passenger airliner, we would need to have chemistries that could deliver 700 or 800 watt hours per kilo, whereas at the moment, 300s, at low 300s is what's commercially available. That's almost a 3 times increase in energy density over where we are today. That is a big hill to challenge. big challenge to climb that hill. And I do make a point that I often make this in conferences, is that in the last 240 years, there's been 5 fundamental changes in energy storage technology. Starting with the Volta pile and then going to lead acid batteries, which remained a curiosity on the desk, on the scientist's bench, until steam powered generators were invented to charge them up. So we couldn't even use the technology when it was available. And then through things like NiCad and nickel metal hydride, and then onto the current generation of lithium ion cells that's being developed. So there's a significant gap between these major technology steps, and we can't expect the next one to come along by next Tuesday. It's going to take a bit of effort and a bit of time to get there. But we have world-leading scientists like Mauro and his colleagues right around the world that are working very hard on trying to solve those issues.
Okay, I mean, I love the back and forth, both complementing each other. It feels like I don't even need to be here. Now, in terms of making batteries, I mean, we're talking about batteries, and we all love batteries. Batteries are great. Now, Isobel, I see that you have got an OBE in your little Zoom title, even putting it there. I don't know what that stands for. I'm going to assume it stands for Overachieving Battery Expert. So with that in mind, could you tell us, what is the process in making a battery? How does one make a battery?
Well, the OBE bit is a little bit of an out-of-date thing, really. The Officer of Order of the British Empire, so it's recognition by the country for my efforts in the battery industry, or not giving up. It was one of the two. I'm still here at the end of the day. So what is involved in making, well, let's talk about the current generations. I think if you go to solid state, there are completely new methods of manufacturing that are going to be required to be able to achieve that. And but some of those things haven't yet been fully figured out. But if you look at standard lithium-ion battery technology, fundamentally it hasn't changed for the last 20 years in its basic concept. When Sony first took on the patent that was developed by John Goodenough and ended up licensee for that technology, they were scratching their heads and wondering how they could get these materials coated onto the electrodes that were required to make the jelly rolls, to make the cylindrical cells like these. And they happened to remember that they had some old magnetic tape processing reel-to-reel coaters within their company, and they decided they were going to utilize that. Fundamentally, that's 1970s technology, and we still use exactly the same process today. We have giant mixers, and they can be the batch or continuous mixers, where we put the anode and the cathode material into them. We also put the solvent that we need to use to liquefy that, to get it down onto the electrodes, and we add in additives and binders and various different conductive elements that we need to make these electrodes work and perform as batteries. We then coat that using a slot die coating machine on a reel-to-reel coater, and we flash off the solvent. And these days we try and recover as much of that solvent as possible. I think we recover about 98% and reuse it back in the process. There's no emissions from the facility from solvents or chemicals. And after we've dried it, we coil it up onto a big coil, and we then slit that coil. We'll cut those electrodes down into specified widths that fit within the cell. And then they will be wound, if it's a cylindrical cell, they'll be wound into a jelly roll. So you have the anode and the cathode and the separator being wound together. Or if it's going into a prismatic or a pouch cell, generally it's a stacked electrode between the anode and the cathode. We have some separators. But that gets put into a can. It then goes to a can finishing line, where the can gets assembled and the electrolyte is injected in. And then we go through probably the biggest bottleneck of any manufacturing process that you can imagine, which is a formation agent test area. It's where we're forming the solid electrolyte interface on the anode, which is really critical to the safe working of the battery. And we're also starting to do some cycling to charge and discharge and make sure the cell is working perfectly. And we're aging the cell as well. We're getting over that initial capacity loss in that formation step to get to a stable capacity. And we're doing an awful lot of testing to make sure that the battery is performing as we expect and within specifications. And then we ship it out to either the automotive OEM or the aeroplane manufacturer, hopefully in the future, or the battery energy storage company, who will then assemble it into a modular pack. And that will be fitted to the vehicle or to the stationary energy storage unit for use.
I know these things take a lot of work, but to hear all of the steps, and you're saying that's a simplified version of it, like, I feel as though I would have a lot easier time if you just told me batteries were made of magic. Like, if you just told me that this is a long con, Mauro secretly, you're a magician. That's what I'd be happier going with. So to bring it back to, the future and as we move forward with battery technology in any sense, from a consumer sense to, larger sort of manufacturer business to business, or, in electric cars, will future battery technology enable batteries to charge faster? Like, will they be able to charge faster? Or will it be a case of they just hold a lot more when they do charge? Like, what will charging look like in the future, Mauro?
That's a very, very good question, because often the two are correlated. So if you're trying to get more energy out, you need to compromise on power. So the amount of time you actually requires to charge. So that often comes at a compromise with the current chemistry. What we are working on, and hence again, we're bringing it back to solid state. And maybe you're probably understanding now why. By replacing the liquid with the solid, we could also, in principle, charge these batteries faster. So without getting overly technical, but again, as you mentioned, it's a Royal Society. Some of our core chemists would like to know maybe more. In a normal liquid electrolyte, when you're applying a current, you form what is known a concentration gradient. So you have a lithium concentration of electrolyte that is different from your cathode to the anode material, and vice versa when you charge and discharge, right? This concentration gradient leads to all sorts of problems that result in poor charging performance. In a solid electrolyte, in particular ceramic solid electrolytes, only lithium ions are mobile. So in principle, we do not form these concentration gradients, and we should be able to charge and discharge faster. I say should, we already proven that it's definitely possible. There are also some startups out there claiming to be able to charge and discharge their batteries very, very fast, right? It's very difficult for us to tell, until we actually test their batteries, how they look like, what they actually have in there. I think from a fundamental science point of view, that should be possible. The challenges are several, and maybe, again, your audience should be interested, mostly lie at the interfaces. Isobel mentioned earlier about this SEI, the solid electrolyte interface. Very often, our electrolytes, and it's the same for a solid, is not stable in contact with the very high energy materials, both negative and positive electron. In particular, metallic lithium, extremely reactive, and you form interfaces in contact with your electrolyte, which is particularly challenging in a liquid. Hence, formation cycle, make sure that we form it right. Otherwise, affecting, performance and safety. And it's also important in the case of a solid electrolyte. So understanding what's happening at interfaces between active material and solid electrolytes is definitely one of the key points. And again, the challenge that we have on top of a normal liquid is that mechanics also becomes particularly relevant. So if you can imagine having a cathode materials on a lithium metal that changes volume every time you insert and de-insert lithium, if that active material is surrounded by a liquid, you can maintain a very good contact quite easily. If you have two solids in contact, you can imagine it's going to be difficult to maintain that contact as we charge and discharge. So there's a whole new field of the electrochemical and battery community, which is actually called electrochem-mechanics, where we're trying to link electrochemistry, chemistry, and mechanics to understand these problems and hopefully come up with solutions as well.
Yeah, there's also some other things that are quite important. Generally, if you try to do anything fast in the battery world, it generates heat. And heat is the enemy of most energy storage technologies, especially the electrochemical ones. So as we increase the charge rate and we shorten the charge time, the heat generation within the cell can really start to shorten the life. So we need to make sure that if we do fast charge, we're not doing it too often. And when we do it, we start at the right temperature point, because coming back to the SEI layer problem, you end up with an efficiency in that layer which reduces as the temperature goes down. The hotter it is, the better it gets. So you end up with more better kinetics in the material. But as you get colder and you start getting below 10 degrees Celsius, then you start to have to slow your charge time down, and certainly below zero, where that SCI layer, in effect, again, oversimplifying it, I apologize, Mauro, but it's fundamentally shrinking, and you end up with lithium metal being plated. So you have ionic lithium, clated and intercalated, and it will start to plate out on the anode, which is a significant safety problem. So we've got a couple of things that we need to manage. We've got to make sure that the temperature for fast charge is in the right sweet spot. It's not too cold. It's a kind of temperature where the efficiency of the charge process is going to be meaningful. And then we've got the problem of the bulk charge. So, the concentration gradients that the Mauro was talking about, and some of the other kinetics within the charge process, means that you hit a voltage lid pretty quickly on the bulk charge. So you can generally get up to 80% state of charge fairly quickly. But then you have to float taper. You hold the voltage and reduce the current until as the charge percentage increases. And generally that can actually be quite a long process. So you'll often see that the automotive manufacturers will say something like 10 to 80% charge in 20 minutes. That may be true, but if you then hold it to 100% charge, you could be sat there for another 30 or 40 minutes, sometimes even longer, and to get the full charge into the vehicle. So these are the things that we've got to manage as technologists and scientists and engineers and the academics in the battery world, is try to figure out some of these problems and how we can get to a much more practical cell configuration and chemistry mix that's going to allow us to do things faster.
I suppose, Isobel and Mauro, you both sort of explained it a little bit there. Like, are we going to get to a point with battery technology where, I can charge my car, my electric vehicle, much in the same way as I would with my regular petrol car or diesel car? You're standing at the pump for maybe 30 seconds to a minute. Like, are we ever going to get to a point where it's not a really, really long time?
You want to take that one, Isabel? I mean, minutes, yes. 1 minute, I don't know if you're asking me, that's going to be very, very difficult. But in the order of 10 minutes, definitely. I think, as Isabel mentioned, we are not that far. It depends on what you mean with charging. If you go 0 to 100, that will take a little longer, and maybe solid state will come into play. If you're thinking at 10 to 80% and your normal day-to-day usage, you are not that far off.
Heading towards 10 minutes is I think, something that's within the realms of possibility. As I said, we're already working on technology that will do that in 10 to 80%. But the other side of the coin is just think about how much energy you've got to deliver to be able to do that. If you have a 100 kilowatt battery pack and you want to charge it in 5 minutes, that's an enormous amount of power to deliver in 5 minutes. And if you look at the upgrade cost to upgrade the power supply to these fast charging stations, there's actually a limit to what is affordable. So currently you've got 350 kilowatt chargers out there, which is like the gold standard. That's what I use for the vehicles that I've got, and I get 270 kilowatts as a peak charge rate, which means that I can pretty much get to 80% in 18, 20 minutes. If I double that to 700 kilowatts, just the power supply to the charge station is going to be enormous. There's practical limits to this.
I like what you've done. Both of you have given really lovely, like really well thought out answers, which essentially boil down to, yes, okay, but why? What? No, which is nice. I appreciate that. Now, you're really talking about cutting edge technology here. Like, this to me is like brain blowing. Do you think that like there's going to be a real trickle down effect from the stuff that both of you are doing? Because right now we're thinking about, electric vehicles and whatnot. But like, do you see like long-term effects, like new technologies being available to the public based on new battery technology?
Interesting question.
I mean, I think I would definitely, we already touched on electrification of flight. I mean, yes, I mean, it's not a completely new technology we already have, but that's definitely something that could be, revolutionized also in the way we travel. Specific new application you probably mean that will be empowered by the novel chemistry that we use. That's a good question.
We're physics and chemistry limited, I think is one of the fundamental issues. If we find some new realm of physics, then maybe we can move on to something that's orders of magnitude better than where we are today. For example, dilithium crystals and Star Trek and warp drive. You need a step change in physics to be able to get to those kinds of solutions. I think the battery industry has demonstrated over the last 20 years that incremental changes and improvements are pretty critical to enabling new market opportunities to emerge. I think if you're going to be moving something completely revolutionary, electric aviation, for example, medium haul or long haul, of course those things would be great to be able to bring into practical reality. But the kind of technology you need to deliver to be able to make that possible is a big step away from where we are today.
Okay, all right. So I guess that leads to my next question. First one's for Isobel, and the following one is for Mauro. Fundamentally, from an economic scale, is new battery tech gonna make energy cheaper for me, the consumer, in my everyday life? What will new battery technology look like for me in my pitiful pocket?
Again, very interesting question. I think that, as we move away from fossil fuels, we're going to be much more dependent on renewable energy. And those energy sources are intermittent. And at the moment, when the wind blows and the sun shines, it's great to feed it into the grid. But as we drop more of the fossil fuels off the energy grid, we're going to need to have battery technology that's going to smooth out that supply and demand imbalance that you naturally get with renewables. So we're already at the point where wind energy is one of the cheapest methods of producing electricity. And that's been because of the development in the industry over the last 15, 20 years. I see that energy storage is a significant part of that to make sure we've got access to those green electrons when we need them, not just when they're available. And batteries will play a part in that. And I think that, getting to lower cost solutions is going to be quite critical, because somebody has to pay for the capital cost of these at some point. So the lower we can get the capital cost, the less effect it's going to have on your energy bill that you'll pay to your energy provider, and allow and free up the access to that lower cost energy. We're not all lucky in that we can't all have hydroelectric dams in our back garden, which is probably the cheapest way of generating electricity. But certainly battery technology is going to play a part in reducing those costs over time.
Yeah, it also depends on what you mean with cost, right? We do not include often, the consequences of carbon dioxide emission as well on the price of, what we're actually paying now for energy. So I think in our ambition to move towards, our goal of, being completely carbon dioxide neutral, carbon neutral in 2050 in the UK, so it's coming up. It's only 30 years. We might need to pay a price that I think in the long run, though, will pay off. So maybe we'll need to go through a transition. I fully agree with Isobel. If you look at solar and wind, it's as cheap as normal electricity. Look at the situation now with Russia also, and being energetically independent, even moving forward. There are so many advantages that looking simply at the cost that we pay on our day-to-day basis right now without looking at the future is a little short-sighted. I think we should have a longer-term vision and all the benefits that we will all get in the longer run.
This one for you, Mauro. In terms, actually, it's for both of you, but Mauro, I'm going to start with you. In terms of battery technology, battery science, is the UK doing a lot? Is the UK in the top 5 in terms of battery science, or are the breakthroughs going to come from elsewhere?
I think we, especially from a fundamental science point of view, we're definitely up there. I would say us, Germany, US, Japan, Korea, China as well. I think we're probably leading on the fundamental science right now. The funding model also with the introduction of the Faraday Institution, I think, has helped, and it will probably help even more moving forward. It allows us and almost, I wouldn't say force, but it encourages, let's say, academics to work together toward a common goal, which I think is beneficial. And also there is more of a vision for the longer term, which I think that's what's absolutely necessary. We could even do more if it was possible in that sense. We need to have a longer term vision, even the way we fund fundamental research, because that allows for the discovery of the next technology. So I would say from a fundamental science point of view, definitely translating fundamental science into industrially relevant products that we can work on, and we are working on, I would say. Isobel mentioned earlier, the lithium-ion batteries were basically invented, or at least half of it, here in the UK. And then you see, from the commercialization point of view, we didn't really capture the value. And there's all sorts of reasons, why that happened, right? I think we should get even better and turning this fundamental knowledge into products. And I think that Isobel, Britishvolt, new industry coming in, that will definitely facilitate the adoption of what we discover on our day-to-day basis in the lab into something tangible and on the market.
Yeah. So, Isobel, in terms of like the future, just bouncing off of that, like, how important do you reckon that new types of batteries with new forms of chemistry, how important do you think they'll be to the UK economy? I ask you this as our overachieving battery experts.
I don't know about overachieving, trying. I think the point that Mauro made was really valid in that, we invented half of the system here in the UK. We licensed it abroad. We didn't capture the value. Just imagine where the UK would be if we decided to commercialize that. We'd be sat on top of one of the biggest growing energy revolutions in the entire world. I think we need to take some lessons away from that. I think the delivery systems that Mauro refers to, the change away from fundamental research into applied research has been a critical step change for us. So writing the problem statement and providing funding to the researchers and the scientists in the country to say, solve the problem. Let's not just generate some interesting ideas. That's a major step forward because it becomes industry-led. And then backing it up with the wider Faraday Battery Challenge, and I was involved in the technical working groups to decide what that was. But that's a delivery mechanism to get the applied research out into commercial production. And I wouldn't say that we've got a perfect system, but I would say that we've probably got one of the best systems in the world to facilitate that. And I certainly get a lot of comments from my colleagues in the battery community around the world looking at things like the Faraday Institution, UK Battery Industrialization Centre, the collaborative R&D programs and the way they're run. They're going, why haven't we got that in our country? It's just the UK that's leading the way on providing those mechanisms. So fundamentally, that's what we built the Britishvolt proposition on the back of, was the fact that we do have world-leading scientists. We do have a delivery mechanism that's focused on commercialization. And that made it, for us, the best place in the world. So
speaking of the economics of it, now, Mauro, I don't know if you knew this, but underneath your desk right now is a briefcase filled with, I don't know, let's say £500 million. What would you do with that money to advance your research? It's a lot of money. What would you do with it?
Yes, again, I believe that fundamental understanding of the problems is the key to finding a solution, have an edge over competing countries, and then give us an edge then to turn that fundamental knowledge into products. So in that sense, what I would probably think about, what chemistries would I focus my attention on? Maybe what would I prioritize? What I believe has a better chance in the longer run to give us that edge. And I want to go back again to solid state because I think I'm maybe biased. But if you look at all the advantages that it could bring, the combination of energy, power, potentially cost in the longer run, I will definitely invest substantially into that chemistry because I think it could give us that extra step and an extra edge.
Okay, that's a good resounding answer. We don't have to, it's implied that the rest of the money is going to go on charity. So this is my final question for both of you, but Isobel, I'm going to start with you very briefly to round it off. What is one takeaway that you would like? That sounds like I'm going to ask about your favorite chip shop. No, what is one what's one takeaway that you would like listeners of this podcast to leave with based on everything you've spoken about? What's one thing you want them to take away from this?
I think the one thing I would want people to really appreciate is that you don't need to go halfway across the planet to get the technology you need to enable an industry change to happen. We have the knowledge and the capability right here in the UK. And it's a matter of making sure we capitalize on that, we fund it properly, and we get the research, the incredible research that's being done in this amazing place through to commercial production. Because China sitting on top of the battery world does not necessarily need to be the answer.
What about you, Mauro?
I would maybe, again, deliver a message of positivity in the sense that, we are in the midst of a real transition towards the better. So we're improving our planet. There are some challenges that they were trying to solve, right? And maybe we focus too much of our attention on the negative aspects in a way, but the change that we're driving it's a completely revolution of the way we think about energy, we supply energy. We're thinking about the future of our planet. So I would say I would send a message of positivity maybe. And again, we're doing the right work. We're in the right place to carry out this work. So again, maybe again to the listeners, stay positive. We're moving in the right direction.
Look at that. The man's made a battery joke, an ion joke. We love it. Moving in the right direction, staying positive. Thank you. Thank you so much for giving up your time. I really, really appreciate that.
Thank you. Take care. Cheers. Bye-bye.
That's all for this episode of Brought to You by Chemistry. It was produced by Hiran Joshi and Elizabeth Ratcliffe and presented by me, Alex Lathbridge.